Let's change it again. Okay. Hi, everyone. My name is Behnam Askarian, and you can call me Ben or B, Dr. B. And this semester, we'll be teaching linear integrated circuits. I'm just going to go through the syllabus today and a little bit of introduction. My office is in ECS 221J. My email is bscarian@wtamu.edu. And my office number is 806-651-52408. My office hours are Mondays and Wednesdays, 3:30 to 5 p.m., but I'm also available anytime after 9:30 on Mondays and Wednesdays. So Mondays and Wednesdays mornings I'm usually available. And also Tuesday, Thursdays, after 11, from 11 to 1 p.m. I'm also in my office. So if you have any questions, just please stop by. Now for this course, we don't have any required textbooks, but I put some recommended ones that would help you if you want to solve extra problems. Now the recommended text is the Ramakant A, the writer is, and it's from Pearson. But again, it's recommended. It's not a required textbook. I will provide you with all the materials that you need for this class. I've already uploaded the lectures for this class. So if you go on Canvas, you can see the lectures. And every week I would upload new materials. If you want to keep up and solve extra problems, I will also post extra problems as well on Canvas. Now, some course descriptions that we have is this course is the study of IC fabrication and integrated circuits in general. And the main, a big chunk of integrated circuits are operational amplifiers. So 70-80% of this course would be focusing on operational amplifiers. We would also go through analog to digital converters and digital to analog converters, a little bit about that. And also active filters, active low-pass filters, high-pass filters, band-pass filters, oscillators, and timers like 555 timer IC. So it will be a general study of integrated circuits. Please read through the course, learning outcomes and so on. You would find some useful materials over there. The important parts, I'm just going to go through important parts. Some course requirements and the evaluation of this course. The homework is going to be 5%. The design project and lab work is going to be 10%. So I'll put maybe 2 or 3%, I haven't decided yet, on your lab work and your lab reports. And the rest would be on your final project. Maybe I would put like half and half, 5% for the lab work, 5% for the project. Depends on, how advanced and sophisticated your project is. Also, if you do a project that, goes beyond the requirements of the class, I would obviously provide bonus points for that. Now, student involvement, which are quiz, and for the online students, it's going to be weekly quiz. After I post the lectures for that week, the videos, you're going to have a quiz, and you're going to have 1 week to take that quiz. And for you, it's going to be a random quiz that I take in the class. And I would take a quiz today so you would get familiar. For those who already had a class with me, they are a little bit familiar with that, but it's going to be a random quiz that I'm going to take. We're going to have 2 exams. Each exam is going to be 25%. It's going to be 50% in total. And the final exam is going to be 30%. Final exam is going to be a comprehensive exam. It's going to include everything that we learn. So I would highly recommend to study for the midterms. I had a lot of students that hoped that they could compensate in the final exam. The final exam is usually much harder than the midterms, and it's a comprehensive, so it's going to be, more materials to cover, it's going to be much more difficult. The grade scale 90 to 100% is A, 80 to 90 is B, 70 to 80 is C, D is 60 to 70%, and below 60 is F. I think having a D means you should automatically repeat the class as well. I'm not sure about this one, but I have to check with the register and Dr. Subraj about it as well. But C, again, the minimum that you need to get is a 70 to 80%. Now, for homeworks, as soon as I post on homework, you have 10 days to turn in your work. I would not accept late homeworks. It automatically closes. And after that, you're not able to upload. Unless you had like a family emergency or something like that, I would not accept late assignments. Having more than 3 of absence in the class would automatically deduct grades. Obviously, you have quiz for attendance. So if you lose too many classes, you're going to lose that 5%. And on top of that, you're going to lose more grades as well. So because you're going to move again, lose assignments and so on. Now, for homework assignment, you don't need to do it on an engineering paper or something like that. As long as it's clear and it's in a PDF format and I can clearly read it, that's okay. So you would do your homework and you could scan it, or if you're doing it on your tablet, that's even better. As long as it's clear to read, it's okay with me. And again, you have that 10-day window to turn in your homework. Sometimes for the homeworks that need more work, I would give 2 weeks, sometimes even 3 weeks. It depends on the homework as well. For exam policies, we have no makeup quiz or examinations, except we have an unusual case. And you have to have serious reasons behind why you want to take that exam. So sickness or family emergency. Rather than that, I would not accept, and we will not have a makeup exam, and you're going to lose the grade for that. And losing one in midterm is technically, you're going to get very close to failing this class because it's like 25% of the class. And students must have at least a C average on the exams altogether in order to be eligible to pass the course. One important thing that we have changed this semester is about generative AI. Our policy last semester was that it's completely prohibited. You're not allowed to use it. Realize it's a fine line to walk, and some students use AI just for learning purposes. That's completely okay. If you want to use generative AI to explain an example to you or get more materials, or that's completely fine. As long as for learning, it's completely okay. But any use of generative AI for solving problems, assignments, homeworks, exams, especially for online students, is prohibited, and it would result in an automatic fail. I have some tools that we can catch if someone is using generative AI, and if someone is using that on their homework assignments, quiz, exams, it's going to be an automatic failure for them. But if you want, on your homework, if you want to sit together and solve a homework in a group, that's okay with me. And actually, I sometimes encourage that. If you have like very difficult problems, that's completely acceptable, as long as you brainstorm and solve a problem together. But please try not to use generative AI. Our goal here is to learn critical thinking and problem solving. Most of the questions, the equations that you learn in this class, you probably would forget it in a year or two. But the way to solve the problem and understand a circuit or an op-amp, that's going to stick with you. So try to solve the problems on your own, even if it takes 2-3 hours for a single problem. Don't try to memorize anything. Engineering is not something that you can memorize. It's not like history or philosophy. You need to understand the problem. You need to be able to solve the problem. And during the course, I will show you that sometimes a single problem may have multiple ways to solve it. So you need to have that, critical thinking and problem-solving mindset to be able to solve it. And I'll give you multiple examples that you can solve an op-amp using multiple different ways, maybe 5 or 6 different ways, complete different ways to solve it. So again, generative AI is completely prohibited for assignments, quiz, exams, anything. But if it's for learning purposes, it's going to help you learn something or explain more, it's completely fine. Please go and read the risks, the safety and chemical, because you have, as mentioned, for the online in-person students, you have a hands-on experience in the lab. For the online students, it's going to be the lab is going to be simulation, the combination of simulation and building some circuits at home. But for in-person students, you need to read the lab safety. And if you have not done that, please go ahead and do the safety training. Now, the tentative calendar is going to be as follows. So you can see here. First week is going to be introduction and IC classification and some fundamental of fabrications. Second week is going to be introduction to op-amps and the ideal op-amp. Third week is going to be op-amp configuration and the characteristics of an op-amp, an ideal op-amp, and non-ideal op-amp. The fourth week, again, we're going to start with op-amp circuits, and then we're going to have a review for exam number 1 and exam number 1. And we will talk about the semester project. I would highly recommend that you start with your project as soon as possible when you learn the basics, because designing and when you want to print a PCB board, obviously we have a PCB printer here, but it's not very fast or good. We usually outsource the printing. It's usually you can do it on JCBL printer for free. They just charge you a shipping for the first 10 or so. And it's very high quality. But the thing is that usually takes a few weeks. It takes 2 or 3 weeks to get your PCB board. And if there's something wrong with it and you want to alter, change it, it's going to take another 3-4 weeks, and you're going to lose the window to present your final work. So try to start with your project as soon as possible. Then we're going to go through practical limitations of op-amps, their cutoff frequencies and the bandwidth. Week 5 is going to be nonlinear circuits and voltage regulations. And then week 6 is going to be oscillators and frequency generators. Then we're going to talk about active filters, passive and active filters. After that, we have a review for exam number 2 and exam number 2. Again, for those who had class with me already, I would highly recommend that you attend the review sessions, because we're going to solve a lot of problems that are very similar to the exam. It's going to help you a lot on the exam. Week 7 is going to be digital to analog and analog to digital converters. And week 7, we're going to have lab exercise again, and I'm sorry, the 7th chapter. I mixed it with the weeks. The lab exercise means that we're going to have a small lab exam. So I would know, because when you're doing the labs in person, you are doing it in the groups. For online students, it's completely different. And I want to check each student to see how much have you learned in the lab. So we're going to have a lab exercise. I will give you a project, a small, op-amp circuit, and ask everyone to do that individually to see how much they have learned from the lab. Then we have the Thanksgiving break and lab project, a review for the final exam, and finally, we're going to have the final exam at the week 17. Do you have any questions about the syllabus? No? Okay. At any point in the class, if you have any questions, just please stop me I would be happy to answer your questions. Maybe your question is your friend's question as well. I say that a lot. And also, don't think that this question is like a easy question. We don't have anything as an easy or question or something like that. Each question may have a point, very important point. So please stop me at any point if you have any questions during the class. Obviously, English is not my first language, so if you don't understand my accent or something that I'm saying, please tell me and I will repeat it. I would say it in a different way. I will be glad to do that. And another thing that I wanted to mention is about class hours. Again, our class hours for now, it's going to start at 9:30 until 10:30, 10:20, 10:30, before we get it to a certain point that we start the labs. And after that we start the labs, it's going to be 2 sessions. We're going to start with theory, and after that, we're going to have our labs. So without further ado, let's start with the course material. So what is an integrated circuit or an IC? An integrated circuit is defined as a circuit in which all or some of circuit elements are inseparably associated. Something that is integrated, connected to, and you can't take it apart. We will go through some history of integrated circuits, different elements of integrated circuits. What does an active or a passive element mean? And I would show you some videos on the fabrication of ICs and how sophisticated and complicated they have become. Now, in a GPU or a CPU, you can pack 10, 20 billion transistors without the connections and everything. And the size of each transistor has become a few molecules right now. So it's becoming very, very sophisticated. And we want to go through a little bit of history and everything as well. Now, integrated circuits means that we put some elements together. We have different elements. Here are some examples of electrical elements. From left to right, do you know what they are? The one on the left is a resistor, the one in the middle is a capacitor, and the one on the right is an inductor. Do you know why have I put these 3 here? These are the 3 basic elements that we have. And in a lot of filters, we just use these 3 basic elements. But beside these basic elements that we have other elements as well. These basic elements are made out of silicon semiconductors, or insulators and conductors, or just conductors. So we have all 3: insulator, conductor, and semiconductor in this picture. But there are other types of elements as well, which are mainly made out of semiconductors. And this is an example of some of them. And these are, as mentioned, built out of semiconductors, mainly silicon. And we have 2 main types, the N-doped and P-doped, meaning we would inject some impurity in the silicon and create a certain type of semiconductor which has an extra electron or an extra hole. Now, from the top left, you can see some example of diodes. We have different type of diodes, even an LED light emitting diode, which are in some screens, and that's the type of diode as well. And we have power diodes, signal diodes, and so on. We have vacuum lamps, which is an older generation in the middle, top middle of transistors. And we have power regulators. We have transistors, normal transistors, which are different types. We have BJT, bipolar junction transistors. metal oxide MOSFET transistor. And on the bottom left, you can see an IC, and then different components of circuits like 7 segments, LEDs, and sensors. Now, why did I put this in this order? This is the building block from the most simplest to the most, advanced one. So the simplest type of semiconductor that we have is that PN junction, that when you connect a PN semiconductor together, you build a diode. So a diode is technically a combination of two semiconductors that are doped with a with an extra electron and an extra hole. Just give me a second too. So we have a diode. And if you combine two diodes, you can build a transistor. Let me see if I can. It doesn't allow me to do that. Just give me one second. I have to open this again. I apologize. So I can use my pen. Nope, doesn't allow me to do that. So let me try another way. Just give me 1 second. So a semiconductor, which could be a silicon or germanium, usually has a crystal form. And we have the silicon in the middle, and then we have connections to other silicon atoms. But if you add an extra electron, you create an N-doped or N-type. And if you semiconductor, or if you add an extra proton or hole, like boron or other things. So for extra electron, you can add phosphorus or arsenic. And for extra hole or positive, you can add boron, for example. You create a p-type. And if you combine an n-type and a p-type together, you have an NP connection. In between, you have an NP junction. And this is a diode. Now, for a diode, we also can show it like this as well. We have different types of diode. This is a signal diode, or power diode is the same. But we have other type of diodes as well. Can you tell me what type of diode this is, if you remember from electronics? Yes, this is a Zener diode. And where do we use a Zener diode? So a Zener diode is used in reverse. If you may remember, the response voltage current response for a diode looks like this. Normal diode works in this area, but a Zener diode works in the reverse. And it's used for voltage regulation. So if you increase the current, by the way, this is current, this is voltage. If you increase the current, the voltage stays relatively, sorry, this is the voltage and that's the current. So if you increase the current, the voltage stays relatively fixed, usually between like 5 or 6 volts. It's very good if you want to build a voltage regulator. So Zener diode is good for voltage regulator. What about a normal diode, signal diode? A signal diode works in this area, and it works like a one-way valve. It allows current to pass in one direction, and it blocks it from the other direction. So it's like a one-way valve. Now, if I add another N junction to a diode, so we have N, P, and if I add another N, Then I have built a transistor. And this is a BJT transistor, or bipolar junction transistor, BJT, sometimes they call it as well. We have different types like N-type or NPN transistors, which we'll explain, and also PNP transistors. Now, if I put these transistors together, and I show it like this, if I put two transistors together like this, and this is a very famous, type of amplifier, I have built a differential amplifier, okay? So this transistor technically looks like this. I have a PNP, and this one also looks like this, a PNP, or NPN, NPN, NP, NP, and N. Now, if I put this in a package and I add 100 of these, now I have an integrated circuit, or an IC. Now, if I add this IC to another IC, I can build an amplifier, or I can build a sensor, and so on. So you can see the building block of an IC starts with a single silicon, which is N-doped or P-doped. And from that, you can build an diode. You can connect those diodes together technically and build a transistor. And you could put those transistors together to build an IC. And you can use multiple ICs in a package to build a larger system, an integrated circuit system. Like a CPU is technically combined of different parts. You have this CU control unit and the processing unit and so on. It's just not a single unit. So that's the reason we had. I've added each of these. Now, elements and components can also be divided in two main categories. We have active elements and passive elements. Now, what is the difference between an active element and a passive element? An active element produces its own voltage, current, and it could control the output voltage and current. Now, some examples of active elements are transistors, diodes, LEDs, because LEDs, they control the direction and so on of the, it's considered an active element. LEDs, obviously, they produce their own photon or current. Photodiode is a good example as well. You put light on it and it produces a small amount of current. ICs is also an active element. Operational amplifier or op-amps type of IC is also an active element. 7-segment displays and batteries are also active elements. Now, some examples of passive elements are resistors, thermistors, capacitors, inductors, and so on, and transformers, and so on. LDRs are light detecting resistors, and what they do is when you shine light on them, the resistance inside of it would change. I would show you some of these in the lab. They are mainly used for sensing light in these automatic, dusk to dawn lights. They use an LDR. They're used in robotics as well for line following or anything that can detect different lights. It's that are used over there as well. So if you shine light on them, the resistance in the system changes. So therefore, it doesn't produce any of its energy. Now, these two tables shows, the table shows, and these two columns show the different characteristics of active and passive elements. You can see the active element, they produce their own power and voltage and current. The passive ones do not do that. Active elements control the current. Passive elements do not do that. Active elements have function of gain for electronic circuits. Passive elements, they are not able to provide power gain and solely depends upon active devices. The active elements are used for current control and voltage control applications. Passive control elements are used for energy storage, discharge, oscillating, filtering, and phase shift, and so on. One example is capacitors and inductors. Capacitor, mainly it's for storing voltage. Inductor is for current. And you can use them for phase shift if you want to synchronize voltage and current. And they're used a lot in filters as well to be able to store some energy. And obviously some examples as well. Now, this graph, this is an interesting one, shows the basic elements of electronics. We have power sources, which could be AC, DC, like a battery or a generator and so on. We have test equipments like oscillators, oscilloscopes, and DMMs, digital multimeters, function generators, frequency counters, and so on. We have discrete passive components like resistors, capacitors, transformers. We have basic passive circuits. We have output devices. We have input devices like sensors, and so on. You can, read faster than I can. So I'm just going to quickly go through some of them. Now, output devices can also be active passive elements as well. Here you can see some output devices like a speaker, buzzer, DC motor, stepper motor, LED, and so on. Our main focus in this class would be on semiconductors and integrated circuits. So the one in the middle would be our focus in this class, both the analog and digital ones. Now, some basics of semiconductors. You're already familiar with diode. This is an interesting slide that I like to show the students. It's a water analogy of diode. Diode works like a one-way valve. So imagine that we have a one-way valve, and the one-way valve, you can obviously see that you can open it just in one way, and there's a spring. So if the water is coming from top to bottom, it's going to push that valve open and the water is going to pass. But if it comes from the opposite direction, you have a small part over here on the right that you can see that doesn't allow the valve to open. So it's going to be like a one-way valve. Now, for an ideal diode, you won't have any resistance when you're on forward bias, meaning the water is coming from top to bottom on the left one. So therefore, if you just put water in it, it's just going to automatically open. But in real world, you could see that spring has a little bit of resistance. And it's the same thing in diode as well, because you have to have the P holes and N holes move. And that creates a little bit of resistance. And you need a little bit of voltage to be able to overcome that energy. And that's called the forward biasing voltage. A forward bias voltage in a silicon diode is about 0.6 to 0.7 volts, meaning to turn on a diode in forward bias, you need to put 0.6 or 0.7 volt to be able to just turn it on. For a germanium diode, it's a little bit lower, it's 0.3 and 0.4. And also we have a reverse bias as well, meaning in an ideal situation, a diode could endure any voltage in reverse bias. But in real world, what happens if I put too much water pressure on the left from bottom to top? If I put a very high water pressure, what happens to the valve? It's going to break, it's going to explode. So that's a limit of diodes as well. In reverse bias, there's a limit on how much power, voltage, or current you can put in reverse. If it's more than a certain point, the diode breaks down and it's going to destroy the diode and it's not going to work anymore. And that's the main reason of power failure in a lot of power devices as well. You have too much reverse bias and it's going to destroy the diode and the power session doesn't work anymore. Now, this graph shows the meltdown, and you can see these 2 points are the points that after this certain point, it's too much voltage for the diode to handle, and the diode is simply going to melt down. It's going to break. We have it both in reverse and forward bias. The diodes are usually rated for a higher forward voltage bias, so it's like 200, 300 volts forward and 60 or 70 volts in reverse bias. Depending on type of diode, the bigger the diode, usually the size is a good indicator. The bigger, the larger the diode is, you're going to have a higher meltdown voltage on forward and reverse. Those diodes are usually called power diodes. They are used for power system applications. We also have these tiny diodes. Usually some of them are classy, transparent. Those are called signal diodes. Signal diodes are the ones that are used in your phones, computers, and communication systems. Their meltdown voltage is pretty low compared to this power diodes, but they are faster. They have a higher frequency. And I'll explain more about that, those type as well. Now, as I mentioned, the forward bias voltage for silicon is 0.6 around. For Schottky is 0.4. For germanium is 0.32, sometimes 0.4, depending on the transistor, the diode and the type of the doping that it has. Now, as I mentioned, if you combine two diodes together, smash them together, you can build a transistor. We have two types of transistors. We have NPN or PNP transistors. So depending on if the P is sandwiched between two N's, it's called an NPN. If the N is sandwiched between two P's, it's a PNP. The only difference between a PNP and an NPN transistor is in their direction of which the current could pass. I think it's enough for today for the transistors. We're going to have a small quiz, and I want you to get familiar with this quiz. For the online students, it's going to be a different type of quiz, and I will post it for them. So the class is technically done for the online students. And thank you, and I'll see you in the next class.